Hello, my name is Kris Hectors. I'm a PhD student at Ghent University and I will be presenting a summary of our work on modeling nonlinear fatigue damage accumulation in a welded runway girder. This research is part of the Flemish SafeLife project that deals with the development of structural health monitoring techniques for large-scale welded structures. To this end, industrial assets were selected which can be studied and on which the developed techniques can be validated. The main goals of the SafeLife project are to gain improved knowledge on the structural behavior of the asset, identify fatigue critical regions such that available resources can be used more effectively and maintenance costs can be reduced, and finally, to extend the lifetime of the assets. In this presentation, the focus lies on lifetime assessment based on the endurance approach. I will first start with a short introduction. Next, I will discuss the different damage accumulation models. The selected models are then compared based on two case studies. In the first case study, a simple two-level uniaxial block loading is studied, and in the second case study, a welded detail of an operational crane girder is assessed. I will end the presentation with an overview of our conclusions. Most structures and mechanical systems are subjected to irregular or random loads while in operation. To determine the stress reversals that occur in the stress spectrum of the loaded system or structure, the rainflow counting algorithm is used. The rainflow reduces the original spectrum into an equivalent set of stress reversals, categorized in bins for different stress ranges. The rainflow counted spectrum of a component can be used to determine the fatigue damage of the component using Miner's rule. Usually, for design purposes, failure is assumed to occur when the damage equals 1. This can be thought of as assessing what proportion of life is consumed by a linear combination of the stress reversals at varying magnitudes. Although Miner's rule has been adopted by all major standards that deal with metal fatigue, it has several limitations. Numerous variable amplitude test programs were carried out to verify the Miner rule, and in many cases significant discrepancies were found. Certain shortcomings of this rule must be understood in order to arrive at reasonable fatigue life considerations. The main shortcomings are that the damage calculation ignores small cycle damage, is load sequence independent, and does not account for load interaction. Small cycle damage occurs when fatigue damage had already been initiated. Small cycles may not initiate the damage feature, but due to, for example, the stress intensity at a crack, they may cause damage to increase if it already exists. Because Miner's rule is inherently linear and thus load sequence independent, it fails to account for the fact that the damage evolution is mostly nonlinear. Often damage increases only slowly in the beginning, but increases much faster as a component reaches the end of its life. Think of a crack that takes a long time to initiate, but propagates quite fast in the end. Finally, Miner's rule does not account for load interaction effects. The sequence in which high and low stress cycles are applied to a component have been shown to affect the fatigue life quite drastically. In some circumstances, cycles of low stress followed by high stress cause more damage than what would be predicted by Miner's rule. Furthermore, it does not consider the effects of overloads or high stresses, which may result in compressive residual stresses that may retard crack growth. High stress followed by low stress may have less damage due to the presence of compressive residual stresses. Stimulated by such discrepancies, several new models on variable amplitude fatigue have been published. It was our goal to select a number of damage models and see how these compare for simple load sequences and for the assessment of a real structure. I will now discuss the different damage models that we have selected in this study. On this slide, you can see an overview of the damage accumulation models that will be discussed in this study. The table shows some of the basic characteristics of the different damage models. All these models are based on the endurance approach, where fatigue life is calculated using an SN curve. The figure on the right shows an example of how the damage, shown on the vertical axis, evolves for a two-level block loading scheme for the different models. The horizontal axis corresponds to the cumulative cycle ratio. The fatigue driving stress model, shown in orange, cannot be considered as a nonlinear damage model, but rather a piecewise linear damage model. The damage stress model and the damage curve approach clearly show how the damage evolves nonlinearly, being slow to initiate but increasing more rapidly as the damage increases. The modified damage curve approach is not shown on this figure, as it's strictly speaking not a damage model but a lifetime estimation model. As mentioned in the previous slide, the fatigue driving stress approach is a piecewise linear model. The approach is essentially a modification of Miner's rule where load sequence effects are included through a logarithmic ratio of the constant amplitude lifetime of the current loading block and that of the first loading block. The damage curve approach was the first true nonlinear damage model. Here the damage evolution depends on the stress level, as illustrated in the figure. The load sequence effects are accounted for by the alpha parameter. Here, the load sequence effects are always relative to the previously active load block and not to the first load block, as with the fatigue driving stress model. A possible issue of the damage curve approach is its dependency on the initial flaw size A0, which significantly affects the damage result. For all assessments in this study, it was assumed that the initial flaw size was equal to 0. In order to include load interaction effects that are not considered by the original damage curve model, a modified damage curve approach was suggested by Waele and its colleagues. To include load interaction effects, the exponent alpha was modified. The interaction factor defined as the ratio between the stress amplitude of the current loading block and of the previous loading block was added, this to account for the load interaction effects. In order to make a quantitative comparison between the lifetime predictions of the previously introduced damage models, they are first compared to experimental data available in literature. The considered fatigue tests are fully reverse rotating bending fatigue tests on the specimen shown in this slide. 18 two-level block load tests were considered to compare the model's performance. These included 9 high-low and 9 low-high sequences. 3 different stress level combinations were used. The same were used for high-low and low-high, but reversed. Also 3 different cycle ratio combinations were used. The models were used to predict the remaining lifetime after the load block was applied. The results are summarized based on the average prediction error, the standard deviation of the prediction error, and with the figure on the right which shows how the fatigue lifetime estimation of the models compares to the actual experimental lifetimes. From the figure it's clear that none of the models is consistently conservative or non-conservative for that matter. The general agreement found in scientific literature was confirmed again, namely that Miner's rule performs worst, having the largest average error and the largest standard deviation with respect to the prediction error. The damage curve approach was found to be the most accurate model for this case study, exhibiting the smallest average error, the lowest maximum absolute error, and the lowest standard deviation. In the second case study, we look at a crane runway girder. Crane runway girders used in industrial environments are subjected to variable loading conditions. Due to the cyclic nature of the loads, fatigue cracks are a known problem in such structures. The same problem has been observed in the studied crane girder, with cracks originating from different welded joints. A 3D rendered image of the crane is shown for clarity at the top of this slide. At the bottom, some images of the actual structure in question and the occurrent damages are shown. A finite element model of the crane girder was developed in the scope of the SafeLife project. The critical stress concentrations found in the model correspond with the locations where cracks have been observed in the actual structure. The top image shows the global stresses in the crane girder when the applied load corresponds to the most critical position of a maximally loaded crane driving over the girder. Based on the results of the global model and experience with the actual structure, a critical detail was selected and modeled using a submodeling approach. The displacements of the global model are used to drive the boundary conditions of the submodel, which includes the weld geometry. In this way, the local response of the welded detail can be very accurately calculated whilst keeping computational costs low. The submodel is shown in the bottom figure. To determine the stresses at the weld toes, the hotspot stress approach was used in accordance with the IIW recommendations. At this stage, we have not been able to validate the model yet. Therefore, the results in this case study should not be considered as an actual assessment of the crane girder, but as an illustration of the methodology in a kind of virtual lifetime assessment. 9 different load cases were defined based on operational data of the crane girder. These were simulated in the finite element model and used to construct the ray flow counted spectra, shown in the three figures. The results of the lifetime estimations are shown in the table. The SN curve used for the lifetime estimations is the FAT90 IIW SN curve associated with the chosen hotspot stress approach. Lifetimes larger than 10 to the power 12 were considered to be infinite. I want to stress again that the lifetime estimations in this table should not be considered as true lifetimes, since no actual measurements have been performed. This is merely a simulation of an actual lifetime assessment. But nonetheless, the results show that we can see significant discrepancies arise between the model estimations when they are used for lifetime estimations of multi-level block loadings. The discrepancies shown here are much larger than those in the first case study. To conclude the presentation, I will finish with a summary. We compared 4 damage accumulation models to Miner's linear damage accumulation rule using 2 different case studies. Based on the first case study, we found that Miner's rule performs worst and that the damage curve approach performs best, but none of the models is consistently conservative or non-conservative. In the first case study, no very large discrepancies were found between the different models, but this was definitely not the case in the second case study, where a more complex fatigue spectra was analyzed. This shows that there is a clear need for more in-depth studies of nonlinear damage model performance when complex fatigue spectra are considered. Finally, I want to finish by saying that we have fitted the crane runway girder in this study with optical fiber Bragg sensors to measure the strains during daily operations. This in the future will allow us to experimentally validate the finite element model shown in this presentation and to perform a more extended study with actual load data. Thank you for staying with me until the end. If you have any questions, I hope to see you at the conference.